The nature of space has captivated human thought for centuries, intertwining philosophy, science, and art. From ancient civilizations that viewed space as a vast, unchanging expanse to modern theories that depict it as dynamic and intertwined with time, our understanding of space has evolved dramatically. At its core, space is not merely an empty void, it is a complex, multifaceted concept that encompasses various dimensions and properties, influencing everything from the movement of celestial bodies to the very fabric of our daily lives. Historically, early conceptions of space were heavily influenced by philosophical perspectives. Ancient Greeks, such as Aristotle, viewed space as a container for objects, a static backdrop against which events unfolded. This notion persisted for centuries, framing space as an absolute entity separate from the objects it contained. However, this perspective began to shift with the work of thinkers like Isaac Newton, who proposed a more quantitative understanding of space. Newton's formulation of space as a three-dimensional continuum provided a framework for understanding motion and gravitational interactions, laying the groundwork for classical mechanics. With the advent of the 20th century, our understanding of space underwent a revolutionary transformation, particularly through the contributions of Albert Einstein. His theories of relativity fundamentally altered the relationship between space and time. In his special theory of relativity, Einstein introduced the concept of spacetime, a four-dimensional continuum where time is inseparably linked to the three dimensions of space. This radical idea challenged the classical notion of absolute space and time, suggesting that measurements of distance and duration are relative to the observer's state of motion. The implications of this shift were profound, leading to a re-evaluation of fundamental concepts in physics and our understanding of the universe. In this context, space began to be seen as a dynamic entity rather than a static backdrop. Einstein's general theory of relativity further expanded this view by proposing that massive objects, like planets and stars, warp the fabric of spacetime around them. This curvature explains the phenomenon of gravity, revealing that what we perceive as gravitational attraction is, in fact, the result of objects following the geometric contours of curved spacetime. This perspective not only revolutionized physics but also challenged philosophical notions about the nature of reality, suggesting that space is an active participant in the dynamics of the universe. The exploration of space has also been influenced by the advancements in technology. As telescopes improved, astronomers began to observe the universe in unprecedented detail. The discovery of galaxies, black holes, and the cosmic microwave background radiation has provided a richer understanding of the structure and evolution of the cosmos. Each of these discoveries has contributed to a more nuanced view of space, where vast distances and time scales complicate our understanding of the universe. The notion that space is filled with dark matter and dark energy further emphasizes its mysterious nature, as these components remain largely invisible yet dominate the universe's mass-energy content. Beyond the physical sciences, the nature of space has also permeated philosophical inquiry. Philosophers have grappled with questions about the existence and properties of space. Is space an entity in its own right, or is it merely a relational property dependent on the objects it contains? These debates have led to various schools of thought, such as absolute space, which posits that space exists independently of material objects, and relational space, which argues that space is defined by the relationships between objects. Such philosophical explorations highlight the complexities of space, urging us to consider not just its physical properties but also its metaphysical implications. The conceptualization of space has also evolved in the realm of art and literature. Artists and writers have long sought to capture the essence of space, reflecting its vastness and mystery. The Romantic movement, for instance, emphasized the sublime nature of nature, portraying landscapes that evoke feelings of awe and insignificance in the face of vast, open spaces. In literature, authors like H.G. Wells and Arthur C. Clarke explored the themes of space travel and the unknown, pushing the boundaries of imagination and human experience. These artistic interpretations enrich our understanding of space, offering emotional and existential dimensions that complement scientific inquiry. As we advance further into the 21st century, the exploration of space continues to be a frontier of human endeavor. The quest to understand the universe has led to remarkable achievements, including robotic missions to Mars, the landing of rovers on distant celestial bodies, and the detection of exoplanets in habitable zones. These endeavors not only expand our knowledge of space but also raise profound questions about humanity's place in the cosmos. Are we alone in the universe? What does the future hold for our species as we venture beyond our home planet? In this ongoing exploration, the nature of space remains a rich tapestry interwoven with scientific discovery, philosophical inquiry, and artistic expression. Each perspective adds depth to our understanding, challenging us to consider the implications of space not just as a physical entity but as a fundamental aspect of existence itself. The nature of space has long fascinated scientists, philosophers, and thinkers throughout history. From the ancient Greeks to modern physicists, the concept of space has undergone profound transformations as our understanding of the universe has expanded. In its simplest form, space might seem like the empty backdrop against which all physical events unfold, a vast void in which matter and energy exist. However, as modern physics has revealed, space is far more complex and intertwined with the fundamental fabric of reality than it might initially appear. In ancient times, space was often thought of as either a container that held the objects of the universe or a purely abstract concept that existed only in the mind. Aristotle, for example, saw space as a kind of container in which all things exist, with the Earth at the center of a series of concentric celestial spheres. This geocentric view positioned space as a static and unchanging entity, a passive stage for the movements of planets and stars. However, this conception of space was challenged by the likes of Copernicus, Galileo, and Newton during the scientific revolution, leading to a more dynamic and mathematically rigorous understanding of space. Isaac Newton's conception of space marked a significant departure from earlier philosophical ideas. For Newton, space was absolute and independent of the objects within it. He envisioned space as an infinite, unchanging, and immaterial stage on which the events of the universe unfolded. In his view, objects moved through space according to the laws of motion and gravity, but space itself remained unaffected by the presence or movement of matter. This idea of absolute space, coupled with the notion of absolute time, provided a stable framework for Newtonian mechanics, which dominated the scientific understanding of the universe for centuries. However, the Newtonian view of space was not without its challenges. One of the most significant challenges came from the theory of relativity, developed by Albert Einstein in the early 20th century. Einstein's theory fundamentally altered our understanding of space and time, merging them into a single, unified entity known as spacetime. According to Einstein's theory of special relativity, space and time are not absolute, but relative to the observer. This means that the measurements of space, such as distance, and time, such as duration, can vary depending on the relative motion of the observer. In other words, two observers moving at different speeds may perceive time and space differently, a concept that was entirely foreign to the Newtonian framework. Einstein's theory of general relativity further revolutionized the understanding of space by showing that space is not merely a passive backdrop but an active participant in the dynamics of the universe. General relativity describes gravity not as a force that acts across space, but as a curvature of spacetime itself. Massive objects, such as stars and planets, cause spacetime to curve, and this curvature influences the motion of other objects. In this sense, space is not a fixed and empty void, it is a dynamic entity that can be stretched, warped, and distorted by the presence of matter and energy. This insight led to a new understanding of gravity and provided the foundation for modern cosmology, including our understanding of black holes, the expansion of the universe, and the Big Bang. The notion of space as a dynamic and flexible entity raises profound questions about the nature of reality. If space can bend and warp in response to matter and energy, what is space made of? Is it a physical substance, or is it something more abstract and mathematical? These questions remain at the forefront of theoretical physics, and they have led to various speculative ideas about the nature of space at the most fundamental levels. One of the most intriguing ideas in modern physics is the concept of quantum space. In classical physics, space is typically treated as a continuous expanse, meaning that it can be divided into infinitely small portions. However, quantum theory suggests that this may not be the case. In quantum mechanics, certain quantities, such as energy, come in discrete units known as quanta. Some physicists have proposed that space itself might also be quantized, meaning that it is composed of tiny, indivisible units or chunks at the smallest scales. This idea is a central feature of various approaches to quantum gravity, a field that seeks to unify general relativity with quantum mechanics. One of the leading candidates for a theory of quantum gravity is loop quantum gravity, which posits that space is made up of tiny loops or networks of interconnected grains of space. According to this theory, these grains are so small that they are far beyond the reach of current experimental techniques, but their existence would imply that space is not continuous, as it appears at larger scales. Instead, space would have a granular structure at the Planck scale, the smallest scale of length in the universe. Another prominent approach to understanding the quantum nature of space is string theory, which suggests that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings of energy. In string theory, space is not just the arena in which these strings move, it is intimately connected to the vibrations of the strings themselves. Moreover, string theory predicts the existence of additional spatial dimensions beyond the familiar three dimensions of length, width, and height. The exploration of the quantum nature of space also touches on some of the deepest questions in cosmology, including the origin of the universe itself. According to the prevailing Big Bang theory, space and time began to exist around 13.8 billion years ago. Before this event, there was no space as we know it, no vast expanse, no distances to measure, no framework for the movement of matter or energy. The very concept of before the Big Bang is problematic, as time itself is thought to have emerged along with space in the moments following the initial explosion of energy. This raises profound questions about the nature of space. If space had a beginning, what caused it to come into existence? Was there something outside of space, or is such a question meaningless? The idea that space had a beginning also leads to speculation about the ultimate fate of the universe. The discovery that the universe is expanding has led to questions about whether space will continue to expand indefinitely or whether it will eventually contract in a big crunch. Observations of distant galaxies suggest that the expansion of the universe is accelerating, driven by a mysterious force known as dark energy. Dark energy, which makes up about 68% of the total energy content of the universe, is poorly understood, but it appears to be pushing space apart at an ever-increasing rate. If this acceleration continues, space may become so stretched that galaxies, stars, and even atoms are torn apart in a scenario known as the Big Rip. Alternatively, if dark energy behaves differently over time, it is possible that the universe could eventually stop expanding and begin contracting, leading to a collapse of space in a reverse of the Big Bang. The nature of space is also deeply intertwined with the concept of vacuum energy, a term used to describe the energy present in empty space. According to quantum field theory, even what we think of as empty space is not truly empty. It is filled with fluctuating quantum fields and virtual particles that pop in and out of existence. This vacuum energy has measurable effects, such as the Casimir effect, in which two parallel metal plates placed close together in a vacuum experience an attractive force due to the quantum fluctuations between them. The existence of vacuum energy raises the possibility that space itself is not a passive void but a seething, dynamic entity filled with energy and potential. From the Newtonian idea of space as an absolute, unchanging stage to the relativistic view of space as a dynamic, curved fabric, our understanding of space has evolved dramatically over time. Modern physics continues to push the boundaries of this understanding, revealing that space may be quantized, intertwined with time, and filled with unseen energy and dimensions. As our knowledge of the universe deepens, the nature of space remains one of the most profound and enduring questions in science and philosophy. Building upon the evolving understanding of space, the concept becomes even more enigmatic as we delve deeper into the universe's structure and the potential implications of modern physics. The more we study space, the clearer it becomes that what we perceive as empty or static is actually a dynamic and integral part of the cosmos itself. Space is not just a passive stage for matter and energy to interact, but an active participant in shaping their behavior and defining the large-scale structure of the universe. Furthermore, as we explore the universe on different scales, from the subatomic to the cosmological, our understanding of space continues to challenge both common sense and established scientific frameworks. One of the most profound discoveries about space in recent decades has been the realization that the majority of it is filled with components that are invisible and mysterious, dark matter and dark energy. Together, these two phenomena make up the vast majority of the universe's content. Dark matter, which accounts for about 27% of the universe, is a form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes. However, its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Without dark matter, the observed rotation speeds of galaxies and the behavior of large-scale cosmic structures would be impossible to explain. Dark matter's interaction with space is another reminder that what we perceive as empty or void is full of hidden complexities. While we cannot see or directly detect dark matter, it exerts a gravitational pull, shaping the distribution of galaxies and the large-scale structure of the universe. Some scientists propose that dark matter could be composed of exotic particles that interact only weakly with regular matter, while others suggest that it may point to a deeper misunderstanding of gravity itself. In either case, dark matter forces us to reconsider the nature of space as we understand it, as it suggests that the visible matter we are familiar with represents only a small fraction of what exists in the cosmos. Even more mysterious than dark matter is dark energy, which makes up approximately 68% of the universe and is thought to be responsible for the accelerated expansion of space. As mentioned earlier, dark energy is a form of energy that permeates space itself, driving galaxies apart at an increasing rate. Unlike dark matter, which clusters around galaxies and exerts gravitational effects, dark energy appears to act uniformly across space, influencing the universe's expansion on a cosmic scale. The discovery of dark energy in the late 1990s came as a surprise to many physicists, as it fundamentally altered our understanding of the universe's fate. The nature of dark energy is still largely unknown, but it is often associated with the concept of vacuum energy, the idea that even empty space contains a certain amount of energy due to quantum fluctuations. In quantum theory, the vacuum is not truly empty but filled with virtual particles that constantly pop in and out of existence. These fluctuations could, in principle, contribute to the energy density of space, giving rise to the effects we attribute to dark energy. However, current estimates of vacuum energy based on quantum field theory are vastly larger than the observed value of dark energy, suggesting that we are still missing a crucial piece of the puzzle. This discrepancy between theory and observation has led some physicists to propose more radical ideas about the nature of space and dark energy. One possibility is that dark energy might be related to a new, unknown field or force that operates on cosmic scales. Another proposal is that our understanding of gravity, as described by general relativity, may need to be modified at large distances to account for the accelerated expansion of the universe. Such theories, while speculative, highlight how much we still have to learn about the fundamental nature of space. The concept of space becomes even more bewildering when we consider the possibility of multiple universes or the multiverse. According to some interpretations of quantum mechanics and cosmology, our universe may be just one of many universes that exist within a larger multiverse. These universes could have different physical laws, constants, and dimensions of space, leading to a vast and varied landscape of possible realities. In this view, the space we experience is just one manifestation of a much larger and more complex structure. The idea of a multiverse is supported by various theoretical frameworks, including string theory and the theory of cosmic inflation. String theory, as mentioned earlier, suggests that the fundamental constituents of reality are tiny vibrating strings of energy, and it predicts the existence of multiple dimensions of space beyond the three we observe. In some versions of string theory, different configurations of these extra dimensions could give rise to entirely separate universes, each with its own set of physical laws. Cosmic inflation, a theory that describes the rapid expansion of the universe in its earliest moments, also provides a potential mechanism for the creation of multiple universes. According to inflationary theory, the universe underwent an extremely rapid expansion shortly after the Big Bang, stretching space to an enormous size. In some versions of this theory, inflation may have occurred in different regions of space at different rates, leading to the formation of bubble universes that are separate from our own. If this is the case, then space extends far beyond the observable universe, encompassing a potentially infinite number of other universes with different properties. The multiverse hypothesis raises profound philosophical and scientific questions about the nature of space and reality. If space extends into multiple universes, each with its own distinct characteristics, what does that say about the fundamental nature of space itself? Is space a universal entity that applies to all possible realities, or is it something that can vary from one universe to another? Moreover, if the multiverse exists, can we ever hope to observe or interact with these other universes, or are they forever beyond our reach? Even within our own universe, the idea of extra dimensions of space challenges our perceptions of reality. In everyday life, we experience space as three-dimensional, with the familiar axes of length, width, and height. However, string theory and other models of physics suggest that there may be additional spatial dimensions that are hidden from view. These extra dimensions could be curled up at extremely small scales, making them undetectable with current technology. If space has more than 3 dimensions, then our understanding of geometry, gravity, and even the fundamental forces of nature may need to be reimagined. The exploration of space on the smallest scales brings us to the concept of quantum foam, a term used to describe the hypothesized structure of spacetime at the Planck scale. At this incredibly small scale, around 10 to the power of -35 meters, quantum effects are expected to dominate, causing spacetime to fluctuate wildly. In this view, space is not smooth and continuous but instead filled with tiny, ever-changing bubbles of spacetime that emerge and disappear on extremely short time scales. This quantum foam could represent the underlying fabric of space, a seething sea of energy and particles that gives rise to the familiar spacetime of general relativity at larger scales. As we continue to reflect on the nature of space, our exploration takes us into even more abstract and speculative realms, where the lines between physics, philosophy, and metaphysics blur. Space, in many ways, serves as the backdrop for the deepest questions we can ask about existence itself. What is the nature of reality? How do the fundamental structures of the universe come into being? And, crucially, does space exist independently of matter, or is it intrinsically tied to the presence of physical entities? These questions have persisted for millennia and remain at the heart of both contemporary physics and philosophical inquiry. One of the most perplexing aspects of space is its apparent emptiness. While it may seem counterintuitive, vast stretches of space appear devoid of any matter or energy. Yet, as we have seen, quantum mechanics teaches us that space is never truly empty. Even in the vacuum of space, there exists a sea of quantum fluctuations, with virtual particles constantly popping in and out of existence. This leads to the concept of the vacuum state, where space is filled with potential energy even in the absence of matter. This quantum vacuum is not just a theoretical construct, it has real, observable consequences, such as the Casimir effect, where two closely spaced metal plates in a vacuum experience a force due to the quantum fluctuations between them. The notion that space is never truly empty also connects to larger questions about the origin of the universe. One of the most profound ideas in modern cosmology is that space itself is capable of creating matter and energy. This concept is rooted in the idea of cosmic inflation, a theory that describes the rapid expansion of space during the earliest moments after the Big Bang. According to this theory, the energy contained within the fabric of space itself can give rise to particles, leading to the creation of all the matter and energy that make up the universe. In this sense, space is not a passive void but an active, creative force, a kind of primordial field from which everything emerges. This idea also brings us to the concept of spacetime geometry and the role it plays in the formation of galaxies, stars, and planets. General relativity tells us that the curvature of spacetime is determined by the distribution of matter and energy. Massive objects, such as stars and black holes, bend and warp the surrounding spacetime, creating the gravitational forces that govern the motions of other objects. On a cosmic scale, this curvature of space is responsible for the large-scale structure of the universe. Galaxies form in regions where the curvature of spacetime creates wells that draw matter together, while the expansion of space itself drives galaxies apart on larger scales. Yet, the relationship between space and matter is not one-sided. While matter influences the curvature of space, space itself can influence the behavior of matter. This is most clearly seen in the phenomenon of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves propagate through space, carrying energy and information about the events that created them. The detection of gravitational waves in 2015, using the LIGO Observatory, provided direct evidence of the dynamic nature of space and confirmed a key prediction of Einstein's general theory of relativity. Gravitational waves are a stark illustration of how space is not a static, immutable entity. Instead, space is flexible and responsive, capable of stretching and contracting in response to cosmic events. This dynamic nature of space challenges our everyday intuitions about the simplicity of the universe. It suggests that space is not merely a backdrop but an integral part of the physical processes that shape the cosmos. Moving from the cosmic to the microscopic, another fascinating aspect of space is how it behaves at the smallest scales. As mentioned previously, quantum mechanics introduces the idea that space may not be continuous but made up of discrete units, or quanta of space. This notion leads to the concept of quantum spacetime, which would behave very differently from the smooth spacetime described by general relativity. At these incredibly small scales, space may become foamy, with tiny fluctuations and distortions that defy our classical understanding of geometry. This quantum foam could be the key to understanding the unification of gravity with the other fundamental forces in nature, such as electromagnetism and the strong and weak nuclear forces. A theory that successfully describes the quantum nature of space is one of the most sought-after goals in modern theoretical physics. This quest is often referred to as the search for quantum gravity, and it has led to several competing theories, including string theory and loop quantum gravity. These theories attempt to reconcile the seemingly incompatible frameworks of quantum mechanics and general relativity, each offering a different perspective on the true nature of space. String theory, for example, posits that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. These strings exist in a higher dimensional space, meaning that the familiar three dimensions of space may be just a small part of a much larger reality. In string theory, space itself is a product of the vibrations and interactions of these strings, suggesting that the geometry of space is not fixed but can change depending on the configuration of the strings. This leads to the possibility that space could have different properties in different regions of the universe or even in different universes. Loop quantum gravity, on the other hand, takes a different approach by treating space as being composed of tiny loops or networks of quantized geometry. In this theory, space is not smooth and continuous but granular at the smallest scales, with a discrete structure that emerges from the underlying quantum processes. This would imply that space itself is subject to quantum rules, with strange and counterintuitive phenomena occurring at the Planck scale, the smallest unit of measurement in the universe. If loop quantum gravity is correct, it could explain how space behaves near singularities, such as the center of a black hole, where the curvature of spacetime becomes infinite according to classical general relativity. The nature of space also invites us to reconsider its relationship with time. In both classical and modern physics, space and time are often treated as separate entities, with space representing the three dimensions in which objects exist, and time representing the progression of events. However, Einstein's theory of special relativity introduced the concept of spacetime, which unifies space and time into a single four-dimensional continuum. In spacetime, the distinction between past, present, and future becomes less clear, as time is treated as another dimension similar to the three spatial dimensions. This unification of space and time leads to some profound implications. For example, in relativity, the passage of time can vary depending on the speed at which an observer is moving relative to another observer. This phenomenon, known as time dilation, shows that time is not an absolute, universal quantity but is relative to the observer's motion through space. Similarly, the curvature of spacetime caused by massive objects can also affect the passage of time, with stronger gravitational fields causing time to pass more slowly,